Okay, so this video is for explaining how we describe the motion using tangential and normal coordinates. So let me just explain this one, so maybe if you just watch this one you will understand why sometimes we need to describe the motion using different coordinate system. First, let me just start with the describing motion using rectangular coordinates. So we have a particle, and then this one is just following the curved path, and then we have rectangular coordinate system y and x, and then as we did, we just make a position vector. Let's say this is a RA over O. And then if this one is moved over a certain period of time, so let's imagine that this one is just moved a little bit here. So let's say this is A prime, and then we can make another position vector. This is R prime A O, A with respect to O. Then this one here, so this the vector. So this is the vector that shows the change of the motion over a certain period of time. So this is called a delta, because that's that's the just change of the vector of the position vector. So let's say this is delta R A O. And then if you just take the velocity, okay, so the velocity of okay, if you just make so if you divide this kind of vector over certain period of time, okay, and then if you make that certain period of time to almost zero, and that's the definitions of derivatives, right? So that's the definition of derivatives of your position vector, and that's the instantaneous velocity of A at a given time. So this is called just this one at an instantaneous velocity. So, but I just want you to think about the direction of the velocity. So this direction, the direction of the velocity, as you see here. So if the A prime is just move a little bit after a very short period of time, then the direction of the velocity must be the tangent to the curved path, right? So which means at this time the velocity of A is just tangent to this curved path. Likewise, if this one is moved along here, at that time the instantaneous velocity of this ball is just tangent to the curved path. Okay. Tangent to the curved path. So the in curvilinear motions, okay, the direction, the velocity tangent to the path. So this is very important. So let's say your particle just moved along this path, then the velocity is just tangent to here. If your particle moved along here, the velocity is always tangent to that the path. Okay, and then this is a tangent tangential direction. Okay, then if you understand this, maybe we can think about one particular motion, which is a circular motion. So let's say your particle just, this is center. Just imagine that your particle just move along this circular motion. So this is circular motion. Then you know that the velocity is tangent. This is the velocity. Okay. Then how about the acceleration? So that's why we want to get the acceleration and velocity using the circular motion. In this particular example, for example, sometimes it's convenient to describe your motion using normal tangential components instead of using rectangular coordinates. So rectangular means I want to make x and y. Okay. So that's my rectangular coordinate system. This is origin. So if you want to describe this motion using your rectangular coordinate system, I need to decompose my vector onto x and y components always. That's my rectangular. So if I want to describe this one, I need to decompose this one is the vx position, and this is vy. So just decomposing the vector along x and y is sometimes necessarily. However, let's say if you want to just describe the motion like the circular motions, then we don't need to necessarily break down the vector onto x and y. Sometimes it's just convenient or more intuitive to describe the motions along the path, right? So if this one is just rotating, maybe you can just simply say that, oh, the velocity along this tangential path, tangent to the path, is a certain value. That's more convenient and easier to describe the motion, right? That's why in a case, rather than using the rectangular coordinate system, we are going to use normal and tangential components. So let me see. In our textbook, we use component. So we describe the motion using normal and tangential components. So which means once you set up the velocity direction, which is tangent to the path, the normal is always the 90 degree with that, perpendicular to the tangential. So here is normal direction. This is normal direction, and this is tangential direction. So this is tangential component, this is normal components. So on this particular example, let's say circular motions, and let's describe this one using normal and tangential components. So let's figure out what's the velocity and what's the accelerations for those kind of circular motions. So first, first, let's just think about the circular motion continuously. So let me just draw this one a little bit better. Okay. So at this time, just for the convenience of my explanations, let me just make a particle here. So let's say this is just moving in this way. So my velocity of this is velocity. And then a certain time later, okay, my velocity pointing this way, right? So let's say this is my A position and this is A prime. And then I can make the line. So this is my radius R. So this is circular motions. So the radius is always the same. And then over a certain period of time, and this is the angular displacement, delta theta. Okay. And then these delta theta motions occur over a certain period of time. So during the period which the point A moved to A prime, that's the time is delta t. Okay, so over the time delta t, the motion A goes to A prime. Okay, then what is the travel distance A from A to A prime? So the travel distance is, this is a travel distance, right? This is travel distance. And then we know that this is velocity v, this is velocity v. So let's say this is, the velocity is always constant right now. And this is my travel distance. Okay. So my travel distance, this blue line, is what? The travel distance is to velocity times and time, right? So my travel distance here is a delta t times the velocity v. That's my travel distance. I know that if this triangle is very large enough, for example, if triangle is very large and this arc length and this travel distance has some difference, obviously, because I'm now looking at this travel distance here. But if this delta theta is very, very small, so just imagine that your kind of triangle has very small angle, then this just right length and also arc doesn't have any big difference. Okay, so that's why for simplicity we just look at the travel distance by multiplying the velocity at this time and delta t. So that's the travel distance. Okay? So I know the length of this part, which is v times delta t. Okay, then let's look at this, our velocity. So at A position, my velocity of here, and A prime position, this is another velocity. So I just want to make the vector here. This is the velocity. And then this is delta theta. That's the same as delta theta. And then this is a v, it just changed the v. And then this is delta v. Okay. And then the length of this delta v, so length of here from here is, the length of this delta v vector is just magnitude of the v. Then if you just look at the two triangles, the one triangle is this one, okay, and the other triangle is this one. I just make a two triangle, and I just wanted to compare the two triangle, this one and this one. So this two triangle is actually has a different size, but it's the similar. The angle is the same, right? So we can just make a simple ratio. So what kind of ratio is this one? So for example, the treble, this one side of the triangle, which is V delta V, that's the side length of this big triangle over the radius R, okay, is equal to, and if you look at this triangle, this side length is delta V, okay, over the length of this side, which is the V, right? So we can simply make a simple ratio using the triangle, using the two different sides of triangle. One triangle coming from this geometry, and the other one coming from your the velocity vector change. So if you just look at this one, I can calculate V square over R is delta V over delta T. And what is this one? So if you make your delta T very small, so which means if you make delta T to almost zero, then this one becomes acceleration of that the rigid body. So this is my acceleration. So acceleration is V2 over R. So now you know that in the circular motion, okay, in the circular motions, when a rigid body shows the velocity along those kind of tangent to the path, the acceleration of that point can be represented by the V squared over R. Okay, and what's the direction of the acceleration? The direction of the acceleration is the same as delta V. So right now, this one is going a little bit down. So at this moment, the direction of the acceleration should be going down. Okay? So if I just clean out this picture, then I can say if the particle just do the circular motions with the velocity of v, then the acceleration is always pointing to the center at this given moment, and this is acceleration. This is normal acceleration, right? So we're still going to use a normal and tangential components when we describe the motions. So right now, this velocity acceleration pointing to the center, which is along the normal direction of your particle. That's why this is AN. AN is always represented by the instantaneous velocity over R. So right now we know that the radius of this circle is R, okay? And then this is a V. Okay, then how about, so far we're just talking about the circular motions, but rather than circular motions, let's think about any general curved motion. So this one just curved, this one, something like that. And then let's say this one is moving to the left side. So I know that when this one is just moved to this way, and this is instantaneous velocity, and this is normal directional accelerations. But this is not circular motion. And then let's say this one is going here, and then how about acceleration of this position? So let's say this position has this kind of velocity. And how about the angular normal accelerations? Normal acceleration is pointing inside, so it should be on here. But right now, since this is not circular motion, so R is not the fixed. R keep changing. So I don't know the R here, but if you just imagine that at this instantaneous position, we can just imagine that there might be some circle here, okay? And only this part is kind of overlapped. So this is circle. So if you know that the radius of this inner circle at this given moment, so let's say this is rho. So and the rho is called radius of curvature, okay? And then AN is equal to the V squared over the rho. But since this is not the same, does not have the same curvature, at any instant point, the rho will keep change. Okay, but as long as we know the rho, we can calculate the normal accelerations using the instantaneous velocity and the rho. Okay. Okay, then let me just give you some example. Okay. Let me give you some example. So example is this one. This is kind of circular motion. Okay, that we have a one boat here, and then this boat has a velocity. The velocity was given. The velocity is 0.0625 t squared. And then the radius is 40 meter. Okay. And then let's find the magnitude of the boat's velocity and acceleration at the instant time t is equal to 10 seconds. So after 10 seconds later, what's the velocity and what's the acceleration of the boat? Okay. And then the velocity is given as this equation. Okay, so right now this is a velocity. So we want to find the velocity after 10 seconds. So we simply put the 10 here. So after 10 seconds, the boat may be on here. Okay. So this V is equal to over 10 seconds. The V is 0.0625, 10 to the square. So this one should be 6.25 meter per second. Okay, so it's very easy. How about the normal component accelerations? So this one, there's the acceleration going down here, and this normal component acceleration is v squared over r, right? So which means we got this velocity 6.25 square, and r is 40. So that's the acceleration, meter per second square. And then unlikely the example that I showed in this video, right now the velocity is given as t squared, and then the tangential velocity is not constant. Tangential velocity is keep changing, which means we can think about the tangential component of acceleration as well. So the tangential component acceleration t is equal to dv over dt, because we know that the velocity is always tangent to the path, right? So that's why tangential acceleration is just dv over dt. So which means 2 times 0.0625 t. So if you want to get the tangential component accelerations, that's the same direction as your velocity. So this is tangential component of accelerations. So that is just equal to 2 times 0.0625 10. Because we want to find the accelerations at the instant time t is equal to 10. So I got tangential component of accelerations and normal component of accelerations, and this is just the velocity tangent to the path. So right now we just described all the motion using a normal and tangential components. And in those kind of circular motions, if the velocity is given tangent to the path, it's more convenient to describe your motion using just normal and tangential components. Sometimes it's more intuitive to describe your motions. And the very last one things that I want to make a point before I close this video. And just think about the physical meaning of normal component of accelerations. Why the acceleration is pointing down? Okay, why? Because acceleration is a time rate change of the velocity. Okay, the velocity is the vector. So even though the velocity magnitude is still same, let's say this is 10 meter per second square, 10 meter per second square, the velocity does not change. So maybe you may think that there's no acceleration at all because the velocity is changed. But the velocity changed. The direction changed, right? So even though the magnitude is the same, the direction changed. That's why the acceleration should be there. That the acceleration that account for the change of the direction is the normal directional acceleration. So that's why in order to change the direction, some acceleration should be pointing to the center. This one accounts for the change of direction of your velocity. And tangential acceleration is just change of the magnitude of the velocity along the tangent. The normal one accounts for the direction change.